Okay, we have this visualization. It should work in theory. Well, while we test it, we could play a Notebook LM 15 minutes. This is just Notebook LM was just given the code for this visualization, so we'll go over it.
Welcome to the deep dive. Have you ever looked at a chart or maybe an image and it just, well, it instantly made sense?
Yeah, it did clicks.
Exactly. Or maybe the opposite happens. It leaves you utterly confused, even though it's supposed to be showing clear data.
Happens all the time.
Today, we're diving deep into something fascinating: the visual language of life. We've got this incredible interactive exploration as our source material. It really shows how scientists take super complex biological data and turn it into images, into plots.
Right.
And our mission today, it's to truly understand not just what these visualizations are showing us, but maybe more importantly, how they're put together.
Yeah, how they're designed.
Because sometimes they reveal these profound truths, right? But other times, maybe without even meaning to, they can kind of obscure things.
Absolutely. It's really about helping you, our listener, become a more, let's say, discerning viewer when you see scientific information. We're going to peel back the layers on the critical choices that scientists make when creating these images.
Choices, like what?
Yeah. Well, like how they choose colors or the type of plot, and how these choices help us understand everything from the electrical buzz in our brains to the really intricate networks inside our bodies. What's truly fascinating, I think, is realizing that good design principles are just as vital here as the scientific discovery itself.
Yeah.
You really can't separate them.
That's a fantastic point to kick off with. It's not just the data, it's how we see the data. Okay, let's unpack this. So before we even jump into the really cool biological images, our source material actually starts with some basics, some fundamental principles of visualization.
The groundwork.
Yeah, and what they show is, honestly, quite eye-opening. The way data is presented can totally change how we understand it. It can even mislead us sometimes.
Exactly right. One of the core ideas they bring up is choosing the right plot. It sounds simple, but it's critical. They use this famous example, maybe you've heard of it, Anscombe's Quartet.
Anscombe's Quartet. Rings a bell, but refresh my memory.
Okay, so imagine you have 4 sets of numbers, 4 data sets, and they look completely different if you actually look at the numbers themselves. They tell very different stories.
Yeah.
But here's the catch. If you just calculate their basic statistics, like the average, the standard deviation, and then you plot only those statistics on a simple bar chart,
Let me guess, they look the same?
they look identical,
Mm.
exactly the same. It's quite striking. And this is where visualization becomes so powerful or potentially dangerous, that simple bar chart. It completely hides the important details about how the data points are actually spread out, the distribution,
So it hides the nuance.
completely.
Yeah.
But if you switch plots, say use a scatter plot instead, or maybe a box plot for those exact same 4 data sets,
Ah, then the differences pop out.
suddenly they become crystal clear. You see the different shapes, the outliers, the real patterns. It's a powerful lesson, isn't it?
Yeah.
About how a picture can either hide the truth or really illuminate it.
That is a huge aha moment. Seriously, it makes you think about every single bar chart you see now. Like, what am I not seeing here?
Precisely. The danger is making decisions based on data that looks the same in one format, when another visual would reveal something totally different.
And it's not just the type of plot you choose, is it? Our source mentions color plays a massive role, too.
Oh, absolutely. Color's huge.
Yeah.
The source emphasizes the critical role of color. And think about it, our eyes are just naturally drawn to patterns in color, right? We're wired that way.
Yeah, definitely.
So if a color scheme is, well, poorly chosen, like the classic rainbow palette or jet, would you get a lot of criticism?
What's wrong with rainbow? It sounds nice.
Well, the problem is it can inadvertently create these false patterns in the data, or it can hide real patterns that are actually there.
Yeah.
Here's the thing. With those rainbow maps, a tiny, maybe insignificant change in the actual data value can cause a huge, sudden jump in color,
Right.
from green straight to yellow.
Ah, I see. So your eye sees a sharp boundary.
Exactly. Your eye gets tricked into seeing a significant boundary or some kind of pattern that isn't actually supported by the numbers. It can lead you down the wrong path.
Okay, so what's the alternative?
That's why people advocate for these perceptually uniform color maps. You might have heard of names like Viridis or Cividis. They're designed very carefully so that the changes in color that you perceive with your eyes directly and accurately match the changes in the underlying data.
So a smooth change in data means a smooth change in color.
Precisely. It prevents your visual system from being fooled by the color scheme itself, It lets the real patterns in the data come through, honestly.
Okay, so taking this all together, for you, our listener, this means whenever you encounter a chart or an image showing complex info, it's really worth pausing
Take a second look.
and ask yourself, is this really showing me the whole story or just, one piece of it? Is the color actually helping me understand, or could it be distracting me, maybe even misleading me? It's about becoming a critical consumer of this visual information.
That's the goal.
Right. So with those fundamental ideas, choosing the right plot, understanding color, let's apply them. Let's turn to how scientists use this visual language to decode the signals of life itself, from our brains, our hearts, our muscles. This is where it gets really cool.
Okay, yeah. Let's start with the brain. We can talk about EEG, electroencephalography.
EEG, measuring brain waves, right?
Essentially, yeah.
Yeah.
It measures the brain's electrical activity from the scalp. And visualizing this data, which is super complex, high-dimensional, it's crucial for understanding a few things. We want to know where activity is happening on the scalp, spatially. We want to know how it changes over time. And we want to know about its different frequencies or rhythms.
Okay, so how do they show that?
Well, one common way is a topographic plot, or topo plot. Think of it like a weather map for the brain's electrical activity.
Ah, okay. Little colorful map on a head shape.
Exactly. You might see, for example, increased alpha band power. That's a specific brain rhythm linked to relaxation, showing up as a hot spot, maybe red or yellow, at the back of the head when someone's just sitting quietly with their eyes closed.
Cool. What else?
Then you have things like time frequency representations. These are more dynamic. They show how those brain rhythms, those oscillatory powers, change second by second, often in response to something happening.
Like seeing a picture or hearing a sound?
Precisely. Our source shows an example called an event-related spectral perturbation, or ERSP. It's a plot that might show, say, an early increase in power in one frequency band right after an event, followed by a decrease a bit later.
So you can see the brain reacting in real time.
You're literally watching the brain's electrical signature unfold as it processes information. It's quite something.
It really is incredible, just seeing the brain at work like that. Okay, moving down from the brain. What about the heart? How does this visual language help us there?
Right, the heart. Well, we typically use ECG, electrocardiography, for its electrical pulses.
The classic heart monitor line.
That's the one. And also PPG, photoplethysmography, which measures changes in blood volume, often from your fingertip or earlobe.
Okay.
And using these together gives us a pretty comprehensive picture of cardiovascular health. Take the annotated ECG waveform. It's a classic visual. It breaks down just a single heartbeat into its key parts.
The bumps and wiggles.
Exactly. The P wave, the QRS complex, and the T wave. Each little bump and dip tells a story.
Like what?
Well, the P wave is the signal for the upper chambers contracting. The QRS complex, that big spike, that's the main pumping chambers, the ventricles contracting. And the T wave shows the heart resetting itself for the next beat.
Huh. All that in one little trace.
But then there's something maybe even more subtle, the Poincaré plot of heart rate variability, or HRV.
Poincaré plot. Sounds fancy. What does it show?
It looks simple, actually. It plots the length of one heartbeat against the length of the very next heartbeat. You end up with a cloud of points.
A cloud? What does the cloud tell you?
The shape of that cloud is incredibly revealing. It tells you about your autonomic nervous system, basically. How well your body is regulating itself, adapting to stress, rest, activity.
How so?
Our source shows a great example. A healthy heart usually makes a sort of dispersed comet-shaped cloud that shows good variability, good adaptability.
Okay.
But a heart in, say, heart failure often shows a very tight, constricted little ball of points. It signals a loss of that crucial flexibility.
Wow. So that simple visual pattern, it's like an instant clue about someone's underlying health.
It's incredibly powerful. Seeing something so subtle, the tiny variations between beats, tells such a big story.
That really is amazing. Okay, brain, heart. What about muscles? How do we visualize their activity?
Right, muscles. For that we use EMG, or electromyography. It records the electrical signals that muscles produce when they contract.
Like an ECG, but for muscles.
Sort of, yeah. And the visualizations can show us the exact timing, the intensity of muscle activation, especially during complex movements like walking. For example, they show EMG envelopes in Gait. This visual basically smooths out the raw EMG signal and compares it between, say, normal walking and maybe someone with a limp.
And you can see the difference.
Oh, clearly. You can see when certain muscles turn on and off during the walking cycle and how strongly they're firing. It highlights the compensation patterns in the limping gait, for instance. Super useful for diagnostics or rehab.
I can imagine.
And then, for a really, really detailed view, There's something called a motor unit firing raster. This is fascinating.
Raster plot.
It shows the
Gotcha.
precise firing times of the exact moments that individual motor units get their command from the nervous system.
What's a motor unit again?
Think of it as one nerve fiber and the small group of muscle fibers it controls. It's like the final command line from the brain to the muscle. And this raster plot looks like a series of dots or ticks over time, showing each time a specific unit fires.
So you can see individual commands lighting up.
Exactly. And as you apply more force, you see more units get recruited, more rows light up on the plot, and the existing ones fire faster, the ticks get closer together. It's a direct window into how the nervous system controls movement at the most fundamental level.
That's incredible detail. Okay, so we've looked at visualizing these invisible signals, electrical activity, muscle commands, but our source also talks about seeing the actual structures, right? Advanced bioimaging.
Yes. This is where things get visually stunning, too. Modern microscopy and these cutting-edge imaging technologies, they've just shattered previous limits. We can now visualize life right down to the nanoscale scales that are just impossibly tiny and often in beautiful 3 dimensions.
In nanoscale. Wow.
And these images, they aren't just scientifically profound, they honestly possess this incredible aesthetic beauty. They reveal the sheer intricate artistry of biology that was completely hidden from us before.
It really sounds like biology meets high art. What are some of the examples or techniques the source highlights here?
They cover a really exciting range, showing what these different tools can reveal. For example, confocal microscopy. This technique gives us really detailed views inside relatively thick samples, getting rid of the blur you'd get with a standard microscope.
How does it do that?
It uses a pinpoint of laser light to scan the sample point by point, and only collects light from a very thin focal plane. It lets you build up these incredibly sharp, detailed 3D images. It was revolutionary for seeing things like the complex branching of developing neurons in a fruit fly embryo, just mapping out those connections with amazing clarity.
Okay, cool. What else?
Then there's light sheet microscopy. This one's great for imaging larger structures, often even in living organisms, over time and in 3D. Instead of blasting the whole sample with light, it illuminates just a thin sheet from the side. This is much gentler on the sample.
Less damaging.
Exactly. Less phototoxicity, less bleaching. So you can watch processes unfold for longer. It's been amazing for seeing things like the development of a cardiac lymphatic network in the heart, this really delicate, intricate system as it actually forms.
Watching biology happen, basically.
Pretty much. They also mentioned scanning electron microscopy, which gives incredible high-res detail of surfaces. They show an image of cholesterol in the liver. Looks almost crystalline.
Right.
And diffusion tensor imaging, DTI, which lets us map the major nerve fiber bundles in the brain, the white matter highways. Visualized as brain tractography, these colorful paths tracing connections.
I've seen those images. They're striking.
They are. And things like photoacoustic imaging, which can give insights into where things like microplastics in tissue might end up. And there's one really unique example they include, self-reflected. It's not just an image, it's an actual art piece.
An art piece.
Yeah, it combines techniques like gilding, like gold leaf, with incredibly detailed scientific illustration of brain circuitry. It's this powerful statement on how art and science can merge to visualize something as complex as the brain.
That sounds incredible. It really underscores the point about art and science, doesn't it?
It really does.
So, looking at all this, what's the big takeaway for us? I mean, it feels like we're just constantly pushing the boundaries of what we can even see, let alone understand about life itself.
That's exactly it. We're developing tools that let us perceive the biological world in ways that were unimaginable just a short time ago. And our understanding is profoundly shaped by our ability to visualize.
Wow. We have covered a lot of ground today. It's been quite a journey.
Yeah.
From those really critical, sometimes subtle principles of just how to plot data accurately,
Like Anscombe's Quartet. Yeah.
to actually witnessing the hidden electrical signals of our brains and hearts, seeing those patterns,
ECGs, HRVs.
and then finally exploring these absolutely breathtaking microscopic landscapes inside our own bodies with advanced imaging.
It really shows that this visual language of life is so much more than just making pretty pictures, right?
Definitely not just pretty pictures.
It's a fundamental tool. It drives discovery. It deepens our understanding, and it's crucial for diagnosis in medicine. And it all hinges on these careful, deliberate choices, from the basic type of graph you pick to the specific colors you use. It's all geared towards making sure the underlying truth of the data is revealed, not hidden.
And connecting back to those initial principles.
Exactly. It underscores how every single decision in how we present data really matters. It has real consequences, from research labs all the way to how the public understands science.
So for you, our listener, maybe the next time you come across a chart or a graph or any image that's presenting scientific or complex information, just remember this visual language of life.
Pause for a second.
Yeah, take that moment. Think critically about how it's being presented, not just what it's showing. Ask yourself those questions we talked about.
Is it clear? Is it potentially misleading? What choices were made here?
And maybe even wonder, what other hidden, invisible aspects of our world are just waiting out there to be understood? If only we can find the right, the most honest, the most insightful way to visualize them.
It makes you think, doesn't it? How this visual language shapes everything.
It really does, how it shapes our understanding of health, of disease,
Yeah,
maybe even consciousness itself. Well, thanks for diving deep with us today.
my pleasure.
We really hope this makes you look at every image, every visualization with a fresh and critically informed eye.
Obviously, there are quite a few issues. It's pretty decent as far as I can tell. This one could have just fit the one screen. The brain rhythms are not really interactive. I mean, it's an actual plot, so you could have done like a simulated, mouse click activity. The certain electrode, for example, something interactive about it. This one meant to actually show you P wave. Well, because when you load the page, it's actually doing like graying out something, but then it stops working. This one's not clear what's currently being displayed, because I understand you can switch between them, but it's not. Yeah, this one, the default setting is not loading, because it's sitting there at 50%, but it meant to have, but it having less points. And all those are copyrighted images, so we cannot actually use them. I think, I'm not sure to actually find if it's a copyrighted material or not, but it looks pretty promising. Should we get a prompt engineer to talk about it? Yeah, go check out the website. Everything we do is available on bionicchaos.com. Go check it out, provide your feedback. This is a good time because everything is under development, so we could actually address your requests, concerns, questions, except, change the color palette. No, we're not doing that. And actually, we will be leaving the current tools as they are, so your feedback, very valuable feedback, will go towards the future development.